So, good evening to everyone. I welcome you all in this session of KTG and Thermodynamics. This is our lecture number 3. I guess it is lecture number 4, na? Okay, so don't worry about that. I'll make it 4. Just give me a second. Okay, so in the previous lecture, we are engaged with the processes in thermodynamics, and we have covered mostly all the process, but the main two process we have left, which is the isothermal process and adiabatic process. Remember? So today, firstly, we will going to complete them, and then we will start the fresh topic, the second law of thermodynamics, heat engine, or try to complete this chapter by today. Okay. So without wasting time, we will just get started with it. Okay. So how is the study going on? Is it well? Going well? I hope it going well. Okay. So firstly, we will talk about isothermal process. Isothermal process is that process in which the temperature remain constant, which means during the process, the temperature of the system will not change. Okay. That process is termed as the isothermal process. Okay. Now we need to calculate the work done in this process. So we can say that if delta T is equals to 0, change in temperature is 0, so PV is equals to constant. And this came from the ideal gas equation, PV is equals to nRT. So if T is constant, these all are constant itself. So PV is equals to a constant. Got it? No. I will derive it by my own. Then you will see in the typed format. Okay, for your better understanding. Now, suppose for isothermal process, work done in isothermal process. Okay, so what is the work done in any thermodynamics process? Work done is given by pressure multiply with the change in volume. Okay, so we can say that here the work done we have is P into delta V. Got it? In this process, temperature is equals to a constant quantity. Okay, so work done we will take here for a very small volume change. We will observe it. So dW we can say it P into dV. Okay, this is the system we have, and this is the gas inside it. This is, let's say, the piston. And it has displaced by this volume. So this much, it's a, let's say it is dx. So if you calculate the work done by F dot dx formula, then also you will left with this pressure into change in volume. So I'm directly using this. Now, this is equation number 1, let's say. So we can say that from ideal gas equation, we can say that PV is equals to nRT, or you can say mu RT, because we have represent the mole in terms of mu. So I am taking here it mu. So what we will do, we will put the value of pressure in terms of volume. Got it? So dW we will have is mu RT divided by V dV. If we integrate it, okay, from volume V1 to volume V2, so the total work done we have is W, and this is 1 by V dV. It is similar to 1 by X dx. So integration of 1 by X dx will become what? The formula is x raised to the power n plus 1 divided by n plus 1. Okay. If you put the value of x raised to the power minus 1 here, so it will become 0. So 1 by x is not given by this formula. Integration of 1 by x is nothing but the ln x. ln, not log. It is ln. Or ln x ko you can also write log x on base e. Okay. So mu rt you can take common. So mu rt you have taken common. Now it will become ln capital V V1 to V2. Now W is equals to mu RT ln V2 minus ln V1. So W you can write as mu RT ln V2 by V1. Any kind of problem in this till now? If you have any kind of problem, clear है यहाँ तक? If it is clear, then give me a thumbs up. Okay. Now, using different color ink. I will take red ink here. Is it visible to you? Virendra, Shiva, is it visible to you? The red ink? Okay. So it is work done finally we will have with mu RT ln V2 by U1. Okay. Now this ln is the base log base EX. We want to convert this base into base 10. So for base 10, we will have a modification here. It will become 2.303 mu RT ln V2 by V1. So this is the final formula for work done. This is the work done in isothermal process. Okay, got it? So you will remember this formula. Although you can replace this V2 and V1 by pressure also. How? Because for state 1, we can write this P1 V1 equals to P2 V2. Okay. So V2 by V1 is equals to P1 by P2. You can put this also in this formula. So it will become W is equals to mu RT ln P1 by P2. So what is given in your question, according to which you will select the work done formula. It is ln V2 by in the final expression it is log. It is log base 10. Absolutely. Because we have converted this ln by multiplying this 2.303 and we have converted this ln in log 10. So this is the work done in isothermal process. Take the screenshot of this expression. Then we will move further. because it is not uh, visible you again if I move to the original screen. So have you taken the screenshot? Give me a thumbs up and rapidly do this because we have a lot to cover today. Okay. Got it? You, I hope you have. Okay, acha, you are returning. Got it. No problem. Take your time. When it's done by your side, give me a thumbs up. Okay. Okay. Got it? So I hope you have written it. Okay. So isothermal process, all the work done we have seen. The graph will be like this. Okay. So graph of one thing that I also want to discuss here, graph. ग्राफ में we will draw the indicator diagram. Indicator diagram में on the vertical axis we have pressure and in the horizontal axis we have this volume. So we know the relationship is PV is equals to constant. So P is equals to some constant, let's say K divided by C. So this is the expression for rectangular hyperbola. So the graph will be like this from 1 to 2. Got it? Although if you want to draw the VT graph and PT graph, you can draw it by yourself because you know that PV is equals to mu RT. So separately, by maintaining the volume constant, pressure is also constant for this. So this is the indicator diagram. Yes, K by V. K is constant, which is you can say, okay, it's K by C. Got it. K is a constant. We will consider it. So graph is like this, PV. Now, if I draw the PT curve forest, PT curve, you will also try to draw PT curve. Because the temperature is constant, so it will vary like this. So for each value, you will see the temperature is constant. So this is 1, 2, 2. Okay. If you draw the VT curve, VT volume temperature, so it will be same this way because the volume is varying but temperature is constant. This is 1, this is 2. Okay. Got it? To try to note these curves. This is very simple curve. Now, so this all we have done. So work done in this process is C ln V2 by V1. C here is the mu RT that we have taken in that expression. Okay, so you can also convert it into pressure formula. Now, adiabatic process. Adiabatic process is that process in which heat transfer is zero. Okay, the heat cannot come inside the system and not go outside the system. The heat transfer is same for it. or zero, you can say. So that process is termed as the adiabatic process, in which there is no heat transfer. Okay. Now, in adiabatic process, energy is transferred to the surrounding only as work, because there is no transfer of heat. So on the energy that can be transmitted in adiabatic processes in terms of work done. Although one very important information I want to give you in this process is, from first law of thermodynamics, we know that delta Q is delta U plus W. So if heat transfer is zero, which means delta Q is zero. So all the work done here will be on the expenses of the internal energy of the system. So system is doing work in adiabatic process will use its internal energy. Okay, because there is no heat you can give. So in the example of bursting of tire, because it takes very rapidly, the process takes place very rapidly, so that it has no time to transfer it to the surrounding. Okay, so system, if it is going very fast change, so system will have any time, it does not have any time to change or transfer the heat to the surrounding. Okay, so that process is termed as adiabatic process. In the bursting of tire, the same phenomena will be there. The bursting of tire will take very small time to be happen. So that process you can take as the adiabatic process, because there will be no heat transfer or no time for heat transfer there. Okay, so it is given by adiabatic process is given by, try to write with me. Okay, so for adiabatic process, it is given by PV raised to the power gamma is equals to constant. Now you will think, what is this gamma? So gamma is the ratio of specific heat at constant volume to the specific heat at constant pressure. So gamma here is the Cp by Cv. We have learned it in the previous session. We have learned about the molar heat capacities and specific heat capacity. So molar heat capacity at constant pressure is Cp, and molar heat capacity at constant volume is Cv. So gamma is nothing but the ratio of these heat capacities. Got it? Now, work done in adiabatic process. Work done in adiabatic process. So same thing we will have here. Let's say this is the cylinder piston arrangement. So we have this gas inside this cylinder. This is the piston we have initially, and the gas has done some work. So the piston will shift to a next position, and it will have covered this volume. So this is, let's say, dV is the volume. So work done is very small for this small change of volume. So we will take it as P into dV. Okay. Now, again, what we will do? We will put the value of pressure in terms of this volume, which is PV raised to the power gamma. So you can write here, this is equation number 1. So PV raised to the power gamma is equals to some constant, let's say C. Okay. So from here you can put P is equals to C upon V raised to the power gamma. Okay. Try to remember that this is gamma. Okay. Now put this value in equation number 1. So what do we have? dW is equals to capital C over V raised to the power gamma into dV. Now integrate it for volume V1 to V2. So you will have total work done W is equals to C, you can take an out common. This will become 1 upon V raised to the power gamma. We will take it upside. It will become V raised to the power minus gamma. So the formula for integration will happen here as V raised to the power minus gamma plus 1. It is same as X raised to the power n plus 1 divided by n plus 1. And n here is minus gamma. So it will become minus gamma plus 1. Now, it is for volume V1 to V2. Now, W is equals to C into, this will become V2 raised to the power 1 minus gamma, I can write it as minus V1 into 1 minus gamma. And in denominator, we will have 1 minus gamma. Okay. Now, what we are wish here, we wish to remove this constant C. So for that, what we will do, this process is taking place from P1 pressure to P2 pressure and V1 volume to V2 volume. So we can say that P1 V1 raised to the power gamma is equals to P2 V2 raised to the power gamma. Okay. Now, we can write here that work done is equals to C upon 1 minus gamma into V2. So in terms of pressure, you can put it V2 raised to the power gamma, okay, will become P1 V1 raised to the power gamma divided by P2. So you can put it here. It is V2 upon V2 raised to the power gamma, because 1 minus power of gamma will go in the denominator, minus V1 over V1 raised to the power gamma. Okay. Now put the value of V2 raised to the power gamma and V1 raised to the power gamma. So what will happen here? Here, if you will see, or one thing you can do here, not doing in that way. This you can write it as V2 by V1 raised to the power gamma is equals to P1 by P2. Okay. Now, work done here will be C into C upon 1 minus gamma, and if you will take V2 by V1 raised to the power gamma as a common, that is possible because of it is V1 V2 over V2 raised to the power gamma minus V1 over V1 raised to the power gamma. Okay. So if you take V2 raised to the power gamma here from this and V1 raised to the power gamma from this, so try to note it up to this. यहाँ तक note कर लिया because I have to rub it off. Okay. So try to note it down. So have you noted down? Have you noted down up to this point? So here the work done will become C upon 1 minus gamma This you can take also in the bottom side, so it will become V2 raised to the power gamma minus 1 minus 1 upon V1 raised to the power gamma minus 1. Okay. Do I remove of this side? This side I am removing. Okay. Okay. Now we know that P1 V1 raised to the power gamma is equals to P2 V2 raised to the power gamma, which is equals to C. So we can put the value of C either P1 V1 raised to the power gamma or P2 V2 raised to the power gamma. So work done we will have as 1 upon 1 minus gamma C upon V2 raised to the power gamma minus 1 minus C upon V1 raised to the power gamma minus 1. Now we wish to put the value of C because here we in the denominator we have V2. So we will put the value of C in which V2 has a quantity. So here P2 V2 raised to the power gamma, we will put it here. Similarly, for this V1, we will put this value. So W will become 1 upon 1 minus gamma P2 V2 raised to the power gamma divided by V2 raised to the power gamma minus 1 minus C1 P1 V1 raised to the power gamma divided by V1 raised to the power gamma minus 1. Now you can see here this is V2 raised to the power gamma into V2 raised to the power minus 1. Okay. So this V2 raised to the power gamma will cancel out this, and this V2 raised to the power minus 1 will go in the upside. Same will happen here. So work done here will be given by 1 upon 1 minus gamma P2 V2 minus P1 V1. So this is the formula for this. Okay. So try to note it down, take the SS of it, screenshot. So if it is okay from your side, give me a thumbs up. I have enabled the reactions for you. You can use it. So Virendra, Santosh, and Shiva. Have you noted down? Shiva? Let me know if I will move forward. Okay, so I hope you have taken the screenshot of it. Now, although the work done you can also given by this formula, again if I talk about, so work done you have calculated 1 upon 1 minus gamma P2 V2 minus P1 V1. Now from ideal gas equation you can write PV is equals to mu RT. So P1 V1 is equals to mu RT1 and P2 V2 is equals to mu RT2. You can put these values. So W work done is also given by 1 upon 1 minus gamma. This mu RT1, T2, sorry, mu RT1. So mu R you can take and common out. So it will become mu R upon 1 minus gamma T2 minus T1. This is also the work done in adiabatic process. Okay. Now, if I talk about the graph, so graph may we will have PV diagram, indicator diagram. So we know that PV raised to the power gamma is equals to constant. So here we will have P C upon V raised to the power gamma. It is looking similar to that expression, but only V raised to the power gamma we will have here. So we can say that it is also like this, but the slope of this curve, previous slide means that one work done wali. So work done you can write from here. It is mu R over 1 minus gamma T2 minus T1. And second formula we will have work done is equals to 1 upon 1 minus gamma P2 V2 minus P1 V1. Okay, so these two formulae we will have. So here the graph will be like similar to you at the isothermal process, but the slope of this graph is somehow different from the, you can say it is different from the slope of isothermal process. Okay, now, so you have noted down. Okay, the same thing is given here. So gamma here you have taken the adiabatic index, which is given by Cp by Cv. Same thing is here. You can note anything if you have left with. Okay, so these are the all the things that I have discussed with you. Here in that expression, it has taken minus is common out. We have found it like this. Okay, by using the ideal gas equation, we can convert it into this expression. Got it? Anytime if you want to move a previous slide, you can tell me. Okay. Now, which process has larger slope on PV diagram? Although I have told you that adiabatic process will take less time, very less time to be happen. So this is very rapid process. Okay. Yeah, very good. Adiabatic process will take very less time. Okay. So the slope of adiabatic process will be greater or less than. Yeah, it has greater slope than isothermal process. So PV is equals to C. If you differentiate this, this will give you PdV plus VdP, and which is for isothermal process. So dP by dV is the slope of PV diagram, which is minus of P by V. Now, if you taken for adiabatic process, PV raised to the power gamma is equals to C is the equation of this process. If you differentiate this, you will have minus gamma times P by V, and gamma is a quantity which is greater than 1. Okay. So the slope of adiabatic process is equals to gamma times of slope of isothermal process. Always remember this. And gamma is greater than 1. So if you compare these two curves, this is for isothermal process and this is for adiabatic process. So if you take the slope of any particular point, this is the value of theta here. And if you take this one, this is the value of theta here. Okay. So slope of adiabatic curve is always greater than the slope of isothermal process. Got it? The question you can see here is the 170 kilojoule of heat is supplied to a system at constant volume. Then the system rejects 180 kilojoule of heat at constant pressure and 40 kilojoule of work is done on it. Okay. Finally, the system is brought back to the initial state by an adiabatic process. So if the initial value of internal energy is 100 kilojoule plus 100, then find out the highest value of internal energy throughout of the cycle. Okay. So in which three process we have, 1 to 2 we will take as a constant volume isochoric process. Then 2 to 3 we will carry out this process as constant pressure. And finally we will take it out completing the cycle with adiabatic process. Okay. So all the data is given to you. Now process 1 to 2 may in the work done in this process 1 to 2 is 0. For isochoric process there is no work done. Work is only done for 2 to 3 and 3 to 1. We will have the formula. So delta Q is equals to delta U. For this, delta Q is 170 kilojoule of heat is supplied to the system. So we will take it positive if it is given to the system. Is equals to U2 minus U1, and U1 we have 100 kilojoule. So this is the value. So final U2 is 270 kilojoule. Okay. So U1 and U2 we have find it out. This is the 270 kilojoule. Now for process 2 to 3, For process 2 to 3, if you will see here, the system rejects 180 kilojoule of it, which is taken out to be negative. Okay. So for process 2 to 3, system reject how much heat? 100 kilojoule. Okay. So minus 100 equals to U3, internal energy of this point, minus internal energy of this point, U3 minus U2, plus minus 40 kilojoule of work is also done by the system. So if it is done by the system, it is taken as negative. So U3 we will have also 130 kilojoule. Now for 3 to 1, you can easily calculate it because potential and internal energy is the path function. Okay, so U3 is 130 kilojoule. So these are the internal energies during these processes. So highest value of internal energy occur at the end of constant volume process. And why it is so? Because if you see delta Q is equals to delta U plus W, and in 1 to 2 isochoric process, there is no work done. So total heat is transferred to changing the internal energy. That is why at the end of this process, we have maximum value of internal energy. Now, summary, you can note it down. Now, if I talk about the next portion of it, it will be heat engine and reverse heat engine. Reverse heat engine is nothing but the refrigerator. Okay. And second law of thermodynamics. So it is refrigerator and heat pump. And then we have a second law of thermodynamics. Now we will deep down into it. What is our learning objective is second law of thermodynamics and engines, reverse heat engine or refrigerator and heat pump, and then Carnot engine. Now we will deal with firstly the engine. So what is an engine? Okay. So engine is a machine or device which convert one form of energy into another form of energy, which is mechanical energy. So engine is such a device which converts any kind of energy into the mechanical work. Okay. So if any device which is converting the heat into heat or any kind of any form of energy into some mechanical work, that particular machine is termed as engine. Okay. So this is the basic picture of an engine, which is IC engine we use in automobiles. So heat engine, like the internal combustion engine, burn a fuel to create heat, which is used to do work. So in heat engine specifically, what do? We give in. So sorry for this technical error. I don't think what is happening to it. Just give me a second. There is some technical error in this. So is the screen is visible to you guys? Please let me know. There is some technical error. I don't think so. What is happening? Okay. Okay. So we are talking about the heat engine. So in heat engine, what happened? We give heat to it and it convert it into the mechanical work. Okay. Now heat engine are of two types: external combustion engine, internal combustion engine. So in external combustion engine, जो fuel है, which burns out of the engine. Okay, externally we burn the fuel, and then we transfer the material into it, into the engine, and we will take the work done of it. But in internal combustion engine, the combustion is happening inside the engine. Okay. So in external combustion engine, what will happen? Firstly, we will take a fuel specifically for steam engine. What will happen? We have a pot of steam, or sorry, water. We will heat it outside. Then we will have the vapors or steam. They'll strike the blades of the engine. The blade will rotate, and finally we will get to the work done. Okay. So this is happening in the external combustion engine. Then internal combustion engine may we will burn it inside the. So you will see this here. This is an example for internal combustion engine. We are burning fuel inside the engine also only. Okay. So this is only just for your knowledge, but we will start the chapter from here. Now the component of heat engine, we will have thermal reservoir. Reservoir is a system in which if you taken some amount of heat, the temperature of the reservoir will not change. This is the property of it. So thermal reservoir is a part of environment which can exchange heat energy with the system, and the temperature is not affected by the quantity of heat supplied to it. Okay. So there are two types here, the heat source and heat sink. Heat source is that from where we take the heat, and heat sink is that from where we reject the heat. Okay. Or you can also set it hot reservoir, or इसे you can heat sink को you can say it is a cold reservoir or surrounding or sink. Okay. Then we have a working fluid. Working fluid is a gas or liquid that primarily transfer the forces. So this working fluid go inside the internal combustion engine, then it burns, and in burning of that, we will get to the work done or mechanical energy. So this is the working fluid there. In petrol engine, what is the working fluid? It is petrol. In diesel engine, what is the working fluid? It is diesel. In steam engine, what is the working fluid? Tell me. In steam engine, what is the working fluid? Shiva, Virendra, and the other two. Yeah, those three four Santosh. Yeah, JNV Ramnagar. Have you any kind of problem, student of JNV Ramnagar? You have risen or raise your. Yeah, very good. Water is the working fluid in that because water is doing work there. Very good. Now heat engine, definition wise you can note it here. It converts the heat or thermal energy into the mechanical energy. Okay. So this is the basic format of engine. This TH is the higher hot reservoir from where we take the heat. So we have taken Q1 heat to the heat engine. Then engine has done some work, and then finally some of the heat is rejected to the sink or atmosphere. So this is the basic format of any engine. This is the heat engine. This is the hot reservoir, and this is sink. So what does the engine do? Engine takes up the heat from hot reservoir, Q1 heat, then it converted into some useful work, and then finally it rejects some heat to the sink. So in also the motorbikes, if you will see, you have traveled 100 kilometer of journey, then you will touch the engine part, so you will feel that it is hot. It is rejecting heat to the system. Sorry, to the surrounding. Okay. Heat engine is always operating in a cycle. If you will see here, first of all, it intakes the fuel from this point. The fuel come inside. Okay, देखो, fuel come inside. Then it compresses the fluid. Then a blast take place with the help of this spark plug. Due to this spark, the gas want to expand because the blast will try to expand the gas because the temperature of the gas rise. As the temperature of gas rise, the pressure of the gas will rise also. So due to this, expansion takes place. Due to that expansion, it exerts the force on the piston. So piston will move down. Okay. Then finally we have uh, burnt gases in that. Then piston will move up due to this flywheel attached to it. And finally, we will have the smoke outside here. Okay. This is the working fluid. Higher temperature पे क्या होगा? Combustion होगा with the help of this spark plug. Okay. Then output we have here an exhaust of burnt gas at temperature TL. Got it? So this continuous intake of the air fuel mixture and exhaust of burnt gases produces a cycle. So it will feel as that it is working in a cycle. Now, efficiency of heat engine is given by eta. So eta here is nothing but the ratio of work output that we have provided by the how much heat we have supplied to the system. So that is the efficiency. So similarly, we can say this is the heat engine. This is high water temperature source. This is lower temperature source. We have taken the heat from hot reservoir, do some work, and then reject it to the system or reject it to the sink, you can say. Okay. So it absorbs the heat from higher temperature, reject the heat to the lower temperature by doing some work. Efficiency, you can say eta of heat engine is work output W divided by heat input. Now, if you will see the energy equivalence equation here, Q1 is the amount of heat that I have taken here. This is nothing but the work done plus Q2 because energy neither be created nor be destroyed. So work done you can say here is equals to Q1 minus Q2. Okay. So if you put this work done in this eta of heat, so it will be Q1 minus Q2, Q1 minus Q2 divided by what is the heat input? What is the heat supplied to the engine? It is Q1. So divided this expression, it will become 1 minus Q2 by Q1. So in thermal expansion or calorimetry, you will see that we can replace this Q2 with the temperatures of it. Okay. So Q is directly proportional to temperature. So eta is equals to 1 minus T2 by T1. This is the final efficiency that you have in a heat engine. Okay. T2 is the temperature of this source where we have reject heat, and T1 is the temperature of this source or the hot reservoir where we have taken the heat. So for you can see here, for eta to be 100%, an engine to be working at 100% efficiency, this T2 should be 0. And T2 is the temperature of surrounding. Okay. Now, the same expression which is given by me. Okay. Now the second law of thermodynamics, and this could be the last of this lecture. Rest of the it will discuss in the later on classes, and we'll start with the KTG. Now, second law of thermodynamics. So in second law of thermodynamics, we have two statements. First is the Canville-Planck statement, or second we have the Clausius statement. So Kelvin-Planck statement of second law says us to that, and it is nothing but the conservation of energy. Conservation of energy. These two laws will change the name, although the law are same. Okay. Now the Kelvin-Planck statement state that, and it is very important to note here, that it is impossible to construct a cyclically operating heat engine, the effect of which is to absorb energy in the form of heat from a single thermal reservoir and to deliver an equivalent amount of work, which is it is impossible to convert all the heat that we received into the work. So that engine is not possible. So if it is possible, we have only this source, we have this heat engine here, we have taken this Q1 amount of heat and then work done. So we will have work is equals to Q. So it is not possible. Some of the heat you have to reject to the atmosphere, which also indirectly says that, yeah, an engine could not be 100% efficient, because efficiency, what is efficiency? It is the work done per unit. What is the input heat supplied? So if work done is same as the heat supplied, so eta would be 1, or in percentage it is 100% efficient. So it is not possible. Okay. So according to Calvin Planck's statement, it is impossible to construct such an engine which is operating in cycle and convert the total heat supplied to the total work done without rejecting heat to the sink. Okay. So it is not possible. Got it? The same thing that I have discussed here. This is the possibility. Now the closest statement that we have, closest statement state that it is not possible to construct a device that operate in a cycle and whose sole effect is to transfer heat from a colder body to a hotter body. Okay, so in easy word, what it is saying that it is impossible to construct such a device which can take heat from the colder temperature or colder source and supply it to the hotter source. क्या ये possible है? Can we take up the heat? Heat will flow always from higher temperature to lower temperature. So it is not possible to construct such a device that could take up heat from the cold source and deliver it to the hot source without any uses of work, without any use of work. Okay, so it is not possible. So this is hotter temperature, this is lower temperature. We have this heat pump which is pumping heat from colder temperature to hotter temperature. Okay, so it is not possible. Okay, what the actually is, can we develop these types of device? Yes, we can make it, but we have to do some work in that. So Q2, Q1, then we have to provide a input work so that by doing some work, it can transfer heat from colder temperature to hotter temperature. And what is the name of that device? What is the name of that device? Which transfer heat from colder place to hotter place? What is the name of that device? Can anyone name that? Student of JNV Ramnagar and Virendra. Student of JNV Baleri, you think? Can you name that device which transfer heat from cold temperature to hot? Anyone? Any kind of idea? And you use it on daily basis. Not heat pump. Its specific name is not heat pump. And you have used it for multiple times. Not oven. It is fridge or refrigerator in your household or in your school canteen. So what is a refrigerator doing? Refrigerator making the place inside chamber, making it more and more cold. So what it is doing? It is taking heat from the cold place and reject it to the atmosphere. Got it? So that device is refrigerator. But to do so, to transfer the heat from lower temperature to hotter temperature, higher temperature, this device consumes some work, and that work done is provided by the motor which is present in the refrigerator, or the compressor, you can say. So we expense some kind of electrical energy to do some work and to transfer it from lower to higher temperature. And it is happened for all the phenomena. Like naturally, water will flow from higher altitude to lower altitude. Okay. But if you want to flow the water from lower altitude to higher altitude, can it be automatically done? Can water do it by own self? No. We have to do some work, and we will do it. In our household, we have tanks, or in your school, you will also have some water tank present on the roof. So, who is delivering the water to that pump, that tank, water tank? The pump that we have. Okay, so pump is doing work to make the water, to transfer the water from lower altitude to higher altitude. Got it? So if you want to work against the nature, you have to do some work. Now, so this is it for today. We have completed the thermodynamics only. Only thing that we left with is refrigerator, heat pump, and Carnot engine. Okay, these three topics not so much of lengthy. So we will cover it into the next class, and we will start the KTG also in that class. Okay, kinetic theory of gases. So I hope you have enjoyed this session. Any kind of doubt you have, you can ask right now. I'm here. Otherwise, you can leave the lecture. It's been over. Thank you so much, guys. Yes, any issue? Thank you, thank you, thank you much. Thank you so much.